So before starting with the schedule model creation and using the scheduling tool, we need to determine what scheduling approach most fits our project circumstances and needs. Now, the precedence diagramming method is commonly referred to as CPM. CPM may use critical chain rolling wave planning, program evaluation and review techniques, and integrated master scheduling. So, the precedence diagramming method, including the critical path approach, is commonly known as the CPM. The CPM may use the critical path method, the critical chain, the rolling wave planning, or the PERT, or even the integrated master scheduling, and the majority of these approaches will be covered in this lecture. Critical interdependencies between activities and sub-projects are required to be included in the schedule. So it's not enough only to determine the activities that will be executing in the project and linking them with logical relationships. We need to determine the interdependencies between the activities and the sub-projects, and also the critical activities and the project. All this will be included in the schedule model. The first step in schedule model creation is selection of an appropriate scheduling approach. Some organizations standardize on a specific software tool and define their own preferred scheduling approaches, applying standards for their use. So before determining what scheduling approach and what scheduling tool you will use for the project, you need to check your organizational process assets and the organizational standards regarding schedule management. In that case, the scheduling approach decision has often already been made, as it is inherent in the tool. So some organizations that are relying on one scheduling tool and they have been using this tool for a lot of projects, they will be determining the scheduling approach as part of this tool. So if I'm using the MS project, for example, I will make sure that this software or this tool includes the CPM if I'm planning to use the CPM. Since it's the most commonly used approach, this practice standard focuses on the critical path method, a predictive approach with considerations related to agile and other emerging approaches. So we will talk about the critical path method and the agile approach in this section. The critical path approach or the critical path method is always used in predictive environments, not in agile environments. CPM refers to the prevalent approach used in modern scheduling tools and helps to identify the shortest time to complete the project. So we defined the critical path method or technique as part of the schedule management approach, and regarding the math calculations relevant to the critical path method, I will be explaining again in the focus on math section. And actually this topic is very important for the exam. You should expect like 10 or 12 questions about the critical path in the PMI-SP exam. The optimal objective of using the CPM is to identify the shortest time to complete the project. The critical path approach is used to derive the critical activities that cannot be delayed without delaying the end date of the project. So we want to determine the shortest time to complete the project. We want to identify the critical activities that cannot be delayed. They don't have any capacity for delay. There is a zero float, and we'll explain the float soon in this lecture. Delaying any activity on the critical path will delay the end date of the project. A basic principle of the critical path method is that each activity is driven by one or more preceding activities. The pure CPM network allows only zero or positive total float on the project critical path. So the float is the amount of time an activity can be delayed without delaying the project, and there are different types of floats. So a float should be zero or positive in the critical path. And one basic principle of this technique is that each activity is driven by one or more preceding activities. Modern critical path method tools accommodate a variety of features to enhance project schedule viability. These features include resources, calendars, like the project activity and resources, constraints, varying definitions of criticality, elapsed durations, lags, leads, external dependencies, activity priorities, and the assignment of actual start and finish dates to the project activities. All these are features that can be applied to your project schedule model using the scheduling tool you are utilizing for your project. Within this modeling process, all of the required project activities and milestones are defined and sequenced to achieve the project objectives. Schedule model creation includes the following processes, which all were covered as part of the schedule management knowledge area and resources management knowledge area in the previous sections. As per the project management body of knowledge edition number 6, we will start with defining the project activities, and then we will sequence these activities and link them with logical relationships. Then we will estimate the activity resources, we will estimate the activity durations, and finally we can develop the schedule model for the project. The schedule model then throughout the project execution will generate the schedule model instances from which presentations are created. The schedule model instances may represent the approved baseline, selected targets, or what-if schedule models. Schedule model creation results in an approved schedule model used by the processes in the executing and monitoring and controlling process groups. So the schedule model itself will be created as part of the planning phase of the project. However, it will be utilized in the execution, monitoring, and controlling processes of the project to report on the schedule performance and to assess the project progress. Now this figure illustrates an overview of the schedule model flow in the project. We will start the project here, and then we will select the scheduling approach, and the scheduling approach might be the CPM, might be the PDM, the precedence diagramming method, or the critical chain, or agile. This approach is usually inherent with the scheduling tool selection, as most modern scheduling tools are software implementations of a particular scheduling approach. So the scheduling tool or software is simply an application of a particular scheduling approach. So selection of a scheduling approach may limit the choice of tools. So you want to make sure that the scheduling tool or software you will be using in your project includes the scheduling approach you selected as part of this software. Then we will enter project specific data like the project scope, resources, WBS, scope statement, etc. to develop the schedule model. Throughout the project execution, this schedule model will be used to take out of it schedule model instances and develop schedule presentations for the stakeholders and the executives of the organization. The scheduler or the planner of the project should update this model on a regular basis and have it maintained and up to date till the project is completed and the schedule model is archived. This figure illustrates flow diagram for the schedule model mapped to the project management body of knowledge guide knowledge areas and processes. So at the right of this figure, you can see the steps of developing the schedule model for the project, and here we can see the processes that are part of the project management body of knowledge edition number 6. So we usually start with defining the project scope before even dealing with the project schedule or thinking about the schedule model. The first step is to determine what will be the project scope. Based on the scope statement developed as an output of this process, we will have the work breakdown structure, and also we will develop the process of acquiring resources in order to know what are the resources available in the project, and we will conduct procurements to know what scope of this project will be executed with vendors or contractors. Now, regarding the schedule model, we will define the milestones through the define activities process, and then we will sequence the activities, linking them with logical relationships. We will estimate the required resources of each activity. We will estimate the duration of each activity, and then we can develop the schedule model, and then we will analyze the schedule model output and approve this schedule model. Before the start of the project execution, this schedule model will be baselined, and this baseline will be used for performance measurements later on. And finally, we will maintain and update the schedule model as part of the control schedule process. CPM, as mentioned earlier, will determine the minimum total project duration and the earliest possible finish date of the project. CPM also determines the amount of scheduling flexibility, total float in the schedule model. To apply CPM, a schedule model that is comprised of project activities will be developed. So the scheduling flexibility, the amount of delay the project can maintain or have without affecting the project end date is known as the total float of the project. And using the schedule approach, the critical path method will allow us to determine the amount of scheduling flexibility. Early start and finish dates are calculated for each activity by means of forward pass from a specific project start date. Late start and finish dates are determined for each project activity by means of backward pass, and both of them were explained earlier in the schedule management knowledge area. We will cover this topic again in the focus on math section. To determine the early start and early finish for each activity, we need to conduct a forward pass from the left to the right, from the start to the finish. And in order to determine the late start and late finish for each activity, we will conduct a backward pass, which is going in reverse from the end back to the start of the project. Now, open ends in a schedule are those activities that lack a predecessor and or a successor activity, thereby creating a hole or gap in the schedule logic from project start to project finish. We don't want to have any open ends in the project. Open ends are those activities that are not linked either to the predecessor or to a successor activity. The only open ends that are acceptable in the schedule model are the project start, because there is nothing before the project start, so there will be no predecessor, and the project finish, because there will be no successor in the project finish. The use of constraints, including leads and lags, should be restricted to those conditions that cannot be adequately defined and modeled by the application of activity logic. Now, CPM illustrates the relationship between activities from left to right, from the start to the end, as time phased in the project, allowing project activities to flow from a project start milestone to the project complete milestone. The relationships between time-phased activities are represented by directional arrows. These directional arrows will indicate the logical relationships between the project activities. In a critical path method, an activity can be connected from either its start or its finish. This allows a start to finish logic presentation with no need to break the work down further. Another characteristic of CPM diagrams is the use of lead and lag components, and we explained what is a lead and what's a lag as different occasions as part of this course. Now, this is an example of a network diagram. Just to recap, before explaining this example, the lead is the time an activity can start before the completion of the previous activity. So if there is a finish to start relationship between activities A and B, that means that activity A should be completed before activity B can start. If there is 3 days of lead, that means that activity B can start, before the completion of activity A by 3 days. This is the lead, while the lag is the waiting time. If there is a lag between activities A and B, it means that even after the completion of activity A, we need to wait for the lag duration before activity B can start. So this is the project network diagram where we can apply the critical path method, and usually each activity will be represented using this diagram showing the link from the predecessor activity. So activity A is a predecessor for both activities B and C, and activity D is a successor for both activities B and C. So here is the early start, here is the early finish that can be determined using forward pass, and here is the late start and late finish that can be determined using a backward pass, and here is the activity name, and here is the duration, and we can put here the float in days and the cost of this activity. Now, another scheduling approach is the critical chain that focuses on the project schedule model activity and resource dependencies. So the key difference between the critical path method and the critical chain approach is that the critical chain will focus on the resources dependencies and availability in the project. The critical chain effectively eliminates most resource contention before the project starts, and it will use buffers in order for project control, and we will explain what are buffers shortly. The critical chain scheduling approach can reduce the project changes and the major source of project cost overruns by improving the project schedule performance. And usually this will be accomplished using, or these results will be accomplished by changing the project measurement and control system along with certain behaviors of the project team and supporting personnel. Considering the availability of resources in the project, the availability of resources that should do the project activities available in the project network diagram, the resultant schedule model may contain a resource-constrained critical path, and it is the starting point for critical chain scheduling. So the key difference again between the critical chain and the critical path is that the critical chain will consider the resource availability and it will rely on something known as the buffers. The critical chain approach is developed from the critical path method and considers the effects of resource allocation, resource leveling, and activity duration uncertainty on the critical path method determined critical path. Critical chain creates an aggressive resource-leveled project schedule. The underpinning principle of the critical chain process lies in the fact that within a systemic chain of actions, there is almost always one action that is constrained or limited by resources, impacting the throughput of the entire chain. So the concept here is having a resource-leveled project schedule and finding out this activity or this action in the flow or in the network diagram that is constrained or limited by the project resources availability. The project end date is defined as the end of the critical chain, including the buffers to account for project risks, uncertainties, and slippages. So we will include in the critical chain some buffers, and these buffers are used to accommodate with any risks that might occur with the project uncertainties and with any possible slippages. During project execution, when activities consume a longer duration than predicted by the critical chain, the project buffer will be gradually consumed in the project. According to the degree of buffer consumption, the project team can address necessary corrective actions from no need to react to planning the response to executing the planned response to recover the project buffer. What action will be taken depends on the consumption of the buffer placed at the end of the project. As long as the total of slippages is less than the buffer, there is a limited effect on project scope, duration, and budget, and this approach is also known as buffer management. The longest resource-leveled path through the schedule, including the buffers, will be known as the critical chain of the project. So the difference between the critical chain and the critical path is the buffers mainly, in addition to the resource-leveled path. It will consider the resources constraints on the project. The critical chain is often different from the critical path in CPM. The defining factors in the critical chain are buffer activities, resources that are not multitasked, resource leveling, and buffer management. These are the key differences between the critical chain and the critical path. Now, the buffers are taken from the planned activity durations and they will not increase the project duration. This is a very important point. Buffers will not increase the project duration. The buffer duration will be taken from the planned activity duration. The critical chain introduces three types of buffers: feeding buffers, resource buffers, and project buffers. So starting with the feeding buffers, as shown in the figure below, feeding buffers are buffers in duration added to the schedule model where chains of non-critical tasks feed into a critical chain task. So as you can see, this is known as the feeding buffers. Feeding buffers are durations added to activities as shown in this schedule model. They will be added to non-critical tasks, but they will lead to a critical chain task. So path A and path B, or activities A and B, are not critical tasks. However, merged path here is a critical task, and the feeding buffer will be added to the non-critical tasks that are predecessors for a critical chain task. Knowing the three types of the buffers and how each of them will be added to the project network diagram is very important for the PMI-SP exam. So this is the feeding buffer. Resource buffers act as early warning signals that ensure the timely availability of project resources by notifying the team of these resource requirements. So they are not durations, they are not buffers with durations, they act only as early warning signals to ensure that the resources needed for an activity are available. They are set along the critical chain to ensure resources are available to work on the activities as soon as they are needed. unlike the project buffers and the feeding buffers, resource buffers are not safety times, so they don't have duration added to the project, and they do not change the elapsed time of the project. And the third type will be the project buffers. Typical project buffers are shown in the figure here. Project buffers are durations, so they are similar to the feeding buffers. They are durations added to the end of the project between the last project activity and the final delivery date. So this is the critical path of the project, showing the last critical activity as activity D, and this is the critical chain with a project buffer, showing a buffer between the final activity of the critical path and the project end date. Now, another scheduling approach used in adaptive life cycles. Projects range from definable work with known scope requirements to high uncertainty work where the project scope and approaches are not as well known. So as explained earlier, projects can be executed using a predictive or a traditional approach if it is from the type of definable work where everything is clear and the scope requirements are not expected to be changed. Also, they can be high uncertainty work where the project scope will be changing throughout the project lifecycle. Agile projects are used to manage high uncertainty work, while traditional and waterfall methods are used to manage definable work. Definable work projects are characterized by procedures and processes that have proved to be successful on similar projects in the past. So there is no need to explore in a definable work project, because we will use processes and procedures that were used earlier and we are sure that they will be successful in our project. The production of a car, electrical appliance, building, or home after the design is complete are examples of definable work that uses a linear approach or a predictive approach. Now you can see this model in front of you, assessing project environments based on two dimensions. The first one is the technical degree of uncertainty, and the second one is the requirements uncertainty. So if we have low uncertainty in terms of requirements and low uncertainty in terms of technicality, this is a simple project and a linear approach will work well here. And we mean with a linear approach a traditional environment or a predictive approach. Now, if there is a mid-level or the level of uncertainty in terms of requirement is moderate, and also it's moderate for the technicality of the project, this is a complicated or a complex environment, and we can use adaptive approaches that work well in a complex or a complicated environment. And if there is a high degree of uncertainty in terms of requirement and high uncertainty in terms of technical degree of the project, this is a chaos status, and it is fundamentally risk, and usually it's managed using an agile approach. New designs, problem solving, and projects not done previously are considered exploratory. They require subject matter experts to collaborate and solve specific problems to create a solution. Examples of high uncertainty work includes software engineering and product design, and they are always managed using adaptive approaches. High uncertainty projects have high rates of change, complexity, and risk. These characteristics can present problems for traditional predictive approaches that aim to manage the bulk of the requirements upfront and control changes through a change request process. So we cannot deal with changes using the formal change control process of a predictive environment in a project where we are expecting a lot of changes. This is why we need to use an agile or adaptive approach that is more flexible in dealing with changes in projects with high uncertainty, in projects with high rates of change, complexity, and risk. Agile is an umbrella term for many adaptive approaches. It allows project managers to quickly adjust to stakeholder needs as well as any feedback the team receives internally or externally. There are many approaches under the Agile umbrella, and two of the more popular approaches are Scrum and Kanban, and we have extreme programming as well. So Agile itself is an umbrella term for many adaptive approaches like the DSDM, FDD, Crystal Methods, Scrum, Kanban, extreme programming, and so on. However, the most popular ones are Scrum, Kanban, and extreme programming. One of the key concepts that we use in adaptive approaches is the rolling wave planning. So rolling wave planning is an iterative planning technique in which the work to be performed in the near term is planned in detail, while work in the future is planned at a lower level of detail. So the idea or the concept behind the rolling wave planning technique is planning in detail only on the near term and planning at a higher level for items on the mid or the long term, as we don't have enough information today in order to plan in detail for the long term in the project. The rolling wave planning technique assumes the project team is very likely to have accurate and detailed information concerning the near-term activities of the current wave and less information about activities in the future waves of the project. And because we have less information about the future waves, we can plan them only at a high level, and we will focus on the detailed planning and the accurate planning for the near-term activities. When using rolling wave planning, it's important to perform the detailed planning at regular intervals. The detailed planning for the next interval needs to be completed before the start of the next wave's execution. The wave durations define the boundaries within which the detailed work will be added at a later date in the project, and I will show you an example of this. For periods beyond the detailed planning wave, activities are listed as planning packages with much less detail. So we will plan in detail only the activities at the near term, and activities beyond the near term will be listed as planning packages with only a high-level plan. These planning packages contain cost and resource information, which becomes fixed in the baseline duration and cost for a critical path approach. When detailed planning takes place, it replaces the planning packages with additional details. So these planning packages that will be planned at a high level at the beginning of the project will be planned in more detail when time comes or when time passes and we reach these planning packages. Rolling wave planning, package 1 decomposed. So for example, we planned earlier for planning package number 1 with less information and less details, and when we reached the time to do the activities A, B, C, and D, we already planned or we detailed the planning package 1 into more detailed activities. And you can see that planning package 2 here and planning package 3 here are only planned at a high level, and we don't know how many activities will be done in each of them. Now when the time comes to execute planning package number 2, we will detail planning package number 2 and we will replace it with activities E, F, and G, and so on. So on the near term, we will have the detailed activities and the detailed plans. On the mid and long term, we will have only planning packages. Another approach, it's not used frequently, but it is explained in the practice standard, the location-based scheduling that is used usually in construction projects. So LBS, or location-based scheduling, was developed to help project managers in the construction industry with workflows and planning. LBS is also known as vertical production method, linear scheduling, repetitive scheduling method, even flow production, and flow line scheduling. So LBS is mainly used in the construction industry. It develops a schedule that shows the location and time of an event in addition to the movement of the crews through time and space. So it will develop a schedule for the project, but this schedule and the activities on this schedule will be linked to the location and time of the event. This is known as the location-based scheduling. So you can see here a location-based schedule model for a construction project showing the excavation and the installation that we are expecting to have at the end of each month. So you can see here that the location is shown on the timeline, not only the activities that are the excavation and the installation. So it's a simple schedule model linking the timeline of the activities with the location where these activities will occur. This approach focuses on optimizing production rates for many resources working in parallel, often on multiple work fronts. The different tasks in the project should proceed in the same flow to create a constant progression without wasted time. Frequently, the model contains a geographical location of the activities in the project. Location-based scheduling is used to plan or record progress on multiple activities that are moving in sequence. This method or the method is visualized by a graphical tool. So usually location-based schedule model is being represented in a visual model. The main attraction of this method over the critical path is its underlying idea of optimizing resource utilization. The progress of the work is easily seen and the sequence of different work activities can be easily understood in the project. This approach is predominantly used in large-scale horizontal construction projects and vertical construction projects. Horizontal like the railways, highways, pipelines, transmission lines, or vertical like the floor-by-floor fit-outs or skyscrapers. Industrial projects sometimes use a hybrid of this approach as well. The last approach is the lean scheduling that is based on the principles of lean project delivery and designed to minimize waste in order to maximize the value. So this is the key concept behind the lean in general, not only the lean scheduling. So lean scheduling is based on minimizing the waste, on maximizing or optimizing the value delivered in the project. To achieve this goal, deliverables are not assigned to the team. Lean scheduling principles point to the importance of limiting queues by pulling work when there is capacity to place the work into the process. So resources will not be assigned to specific activities in the planning phase of the project. Resources will be assigned only when there are items and the resources are available to do these items or to work on these items. The project team members collaborate in pull planning. The lean scheduling is also known as pull planning that is used in the Kanban method. The project team members collaborate in pull planning sessions where the essential activities, durations, and handoffs between trades to complete milestones are well defined in the project. The main steps in the lean schedule: master scheduling that identifies key milestones, essential activities, and phases. This detailed schedule is created by the project team. Phase scheduling is the next step at more detail, uses phases identified from the master schedule, working backward, pulling the duration, sequences, constraints, and coordination in each phase are collaboratively established in the project. The team agrees on the plan and executes as a team. The output from this phase schedule is used to generate look-ahead schedules in the third step, and look-ahead planning maximizes reliability by matching workflow with capacity. Detailed plans for work to be done are established using weekly work plans, and a backlog of ready work will be maintained throughout the project execution. So this is the simple 3 steps of the lean scheduling approach. For the exam, the first part of this lecture was the most important, the critical path and the critical chain.